Welcome to another lesson on permutations and combinations. A very basic topic, so should be a lot of fun. So what's a permutation? A permutation is an arrangement of objects in a specified order. The number of ways of arranging n unlike objects is n factorial. Alright, this question, this exclamation sign simply means n factorial. So for example, 6 factorial would be equal to 6 times 6 minus 1, which is 5, times 6 minus 2, which is 4, and so on, and we multiply until we reach the number 1. Another example, 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So for example, if we're asked to find the number of permutations or arrangements of the letters A, B, and C, we can look at a few methods. Let's look at the first method 1. What we could do is find the different ways we can arrange A, B, C. So we can arrange the letters A, B, C, A, B, C. We can put the A, then the C after. We can begin the arrangement with a B. So we have BCA and BAC. That's another arrangement. Or we could begin the arrangement with a C. So CAB. Or we could have CBA. So that's 1, 2, 3, 4, 5, 6 permutations or arrangements. Another method is simply the formula. Simply the formula. And since we have 3 distinct elements, the formula n factorial, where n is an amount of elements or characters we are arranging, is 3. So that's 3 factorial. And 3 factorial is 3 times 2 times 1. And notice we have 6 different ways of arranging these 3 unlike characters. Or we could use what we call the box method. So this is the formula in factorial, or the box method. We could say, okay, we have 3 items to arrange. In the first slot, we have 3 options, any of 3, A, B, or C. Now, once we put an element in the first slot, and the second slot, we have 2 options, since we have 2 elements remaining. And if we put 2 elements in the first 2 slots, whichever elements, whether A, B, or C, in the last box, we'll only be left with 1 option. So we can multiply 3 times 2 times 1. So there are 6 different ways of arranging these 3 characters, A, B, C, or any 3 characters which are not the same. So notice method 1, we simply list the different arrangements. Method 2 is the formula n factorial, where n is the amount of characters. In this case, we're looking at 3 characters. And method 3, we refer to method 3 as what we call a box method. So here are 3 quick examples for practice. Find the number of arrangements or permutations of the letters of the word Jake. Notice we have 4 characters and all of them are different, so none of them are alike. So let's do the formula. So the formula, number of ways of arranging Jake, is n factorial. In this case, n is 4. So 4 factorial, which is equal to 4 times 3 times 2 times 1. So 4 times 3, 12. 12 times 2, 24. 24 times 1, that's still 24. So there are 24 ways of arranging any 4 unlike characters. Second one, how many 4-digit numbers can be formed using these digits? 2, 4, 5, and 7. Again, 4 characters. So the number of arrangements is 4 factorial. That's 4 times 3 times 2 times 1. 24 just the same. Next, 5 girls and 2 boys are to form a line at the school cafeteria. In how many ways can this line be formed? So 5 girls and 2 boys, that's 7 persons, and all of them are unlike because no 2 persons are the same, even if they are a twin. So the number of different ways of arranging forming this line is 7 distinct characters, so 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, and that's equal to 5040. So there's 5040 ways of forming a line which has 5 girls and 2 boys. Now, what if we're arranging some objects and some of them are alike? So for example, what if we're asked to arrange the letters J, E, E, P? Right? So we notice we have n objects, J, E is there twice, and P. Alright, so P are alike. In this case, we have E are alike. So using the formula, it's n factorial, where n is overall the number of objects. So the number of arrangements for this would be 4 factorial, represented by n in the formula. N is just the total number of objects. And notice E appears twice. So it's 4 factorial divided by one character appeared twice, so it's divided by 2 factorial. Now 4 factorial is 4 times 3 times 2 times 1. 2 factorial, that's 2 times 1. So in the numerator, 2 times 1 divided into 2 times 1 below. So we're left with 4 times 3, 12. So the number of ways of arranging these 4 characters would be 12 ways. What if we are to determine the number of ways of arranging the letters of the word statistics? So notice n, so the number of arrangements, so the number of permutations or arrangements. Notice permutations and arrangements are synonyms in this context. So look, in terms of the n is the total number of characters, so let's count them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters. So 10 factorial over, and let's look at how many are alike now. So look at the S. S appears 3 times. So S is there 3 times. So we have an S here, another S, another S. So we have S appears 3 times. So 3 factorial to represent that. Times T. T also appears 3 times. So T, and T again. So T appears 3 times. So 3 factorial. And I is there twice. So I is there 2 times. So times 2 factorial. That's an extension to the formula. So the total number of characters here is 10. So 10 factorial. And one character, that's the T, appears 3 times. So 3 factorial to represent that. S also appears 3 times. So 3 factorial to represent that. And I appeared twice. So 2 factorial to represent that. So in doing the calculation, 10 factorial, that's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 3 factorial, that's 3 times 2 times 1 times 3 factorial again, that's 3 times 2 times 1 times 2 factorial, that's 2 times 1. So now 3 times 2 times 1, up here cancel, 3 times 2 times 1, we'll cancel here, down here. Here, 3 times 2 times 1, that's 6, we'll cancel 6 up here. And So let's calculate the rest of the numerator. Here 2 times 1, that's 2, divided into 10, so that's over 5. So your solution would be 5 times 9 times 8 times 7 times 5 times 4, which would leave us with 50,400. So 50,400 ways of arranging the letters in the word statistics. Let's write the 5 better. 50,400. Let us look at another example. A 6-digit number is formed from the digits 440, and we have 3 sevens there. Repetitions are not allowed. How many of these 6-digit numbers are divisible by 10? Let's do it a couple of different ways. So for a number to be divisible by 10, it has to end with 0. So 6 digits, so let me put the slots here. So 1, 2, 3, 4, 5, 6. So it has to end with 0. So if you think about it, the 0 will be fixed. So we're really only moving 5 characters. So if you think about it, we're going to be rearranging these 5 characters. Alright, rearranging, of course, 0 will be fixed. So it was rearranging 5 characters here. So in terms of using the formula, 5 factorial, since it's 5 characters, we are moving around. But among the 5 characters, 4 appear twice. So 2 factorial to account for that. And 7 is there 3 times. So 3 factorial to account for that. So the calculation here would be 5 times 4 times 3 times 2 times 1 over 2 factorial, that's 2 times 1, and 3 factorial, that's 3 times 2 times 1. Now up here 3 times 2 times 1, we'll cancel 3 times 2 times 1 down here. In the numerator, we have 5 times 4, which is 20. Denominator, 2 times 1, 2. So 20 divided by 2, 10. So there are 10 ways of getting 6-digit numbers which are divisible by 10. Before we go any further, let's examine the counting principle a little bit. If an event A can occur in m possible ways, and when this has been done, event B can occur in n possible ways, then there are m times n possible ways for both events A and B to occur. And an example here. How many ways can I dress if I have 4 shirts and 3 pants? So if I have 4 shirts and 3 pants, the number of ways I can dress, the number of ways, of different ways I can dress. 4 shirts, so 4 and, so and multiply. So we have 12 different ways we can dress. By the way, if R would add. And that's from probability theory. So if you think about it, if I have 4 shirts, let's say I have 4 shirts. So we have shirt 1, shirt 1, shirt 2, shirt 3, shirt 4. So shirt 1, 4 shirts, right? So shirt 1, I can wear with 3 different pants. P1, P2, and pants 3. Likewise, shirt 2, 3 different pants. Shirt 3, 3 different pants. Shirt 4, 3 different pants. And you'll realize that there are 12 different ways of dressing. Another example. It is known that the password on a computer system contains 3 letters, A, B, C. So the password. So the first 3 characters will be 3 letters A, B, and C. And if you think about it, A, B, and C, we can arrange it as A, C, B, B, C, A, and so on. So 3 characters can be arranged in 6 ways, 3 factorial ways. And after that, followed by these 4 characters. So 1, 2, 3, 4. 1, 2, 3, 4. So we have 4 characters here. And because it's 4 characters, their number of arrangements can be 4 factorial ways. So in terms of a number of possible passwords, so think about it, the password must begin with these 3 letters, A, B, C. So if I should put ACB, BCA, CBA, and so on, that's all different passwords. Alright, since the password would the order of the characters, a different order will give a different password. So 3 characters, 3 factorial. And the password should be completed using the digits 1, 2, 3, 4, 4 characters, and there are 4 factorial ways of arranging these. So the number of passwords we can get, if the passwords must follow the structure, begin with ABC, end with 1, 2, 3, 4, in whatever order, then that's 3 factorial, that's 3 times 2 times 1 times 4 factorial, that's 4 times 3 times 2 times 1, so 3 factorial, 3 times 2 times 1, that's 6, and 4 factorial, 4 times 3 times 2 times 1, that's 24, so 6 times 24 will give us 144. So let us look at a variation to the permutation formula, NPR, and that's when we're selecting R objects out of N distinct objects. And in this case, we use this formula when the order is important. So order matters. There's also another formula that we use when the order is not important, and that's the combination formula, NCR, and that's N factorial over N minus R factorial times R factorial. So this formula is used when the order of a selection does not matter. So we're selecting R objects from N distinct objects. Let us begin with a simple example. How many 2-digit numbers can be formed using the digits 1, 2, 3? So the question is, do we use NPR or do we use NCR? Remember, NPR is when the order matters. So NPR, when the order is important, or the order matters. And NCR, we use this formula when the order does not matter. So order does not matter. Now let's look at the question and get a sense of when we choose which to use. So how many 2-digit numbers can be formed using the digits 1, 2, 3? So we have these digits here, 1, 2, 3, and we want to find out, we want to determine how many 2-digit numbers we can form. Alright, so one option would be 1, 2, but if you switch around these elements 1, 2 and turn it into 2, 1, you see it's a different number. So 12 and 21 are 2 different numbers, even though they are formed by the same 2 digits, 1 and 2. Alright, we could have 1, 3, 3, 1. So you see the order of the digits matter. The order of these characters matter because just the way you arrange them will give you a different number. Also, we could have 2, 3 or 3, 2. So if you think about it, by just listing out the options, there are 6 2-digit numbers we can arrive at using these digits 1, 2, and 3. So the answer is 6. But if we are to use this formula, NPR, so number of digits, so number of 2-digit numbers, using the formula would be NPR, since the order is important. Alright, the order of which we select these 2 elements are important. And notice we have an option of 3 elements, so it's 3, P2. So remember the formula, remember NPR is equal to N factorial over N minus R factorial. So the formula is used, N factorial over N minus R factorial. So in this case, 3P2, that's 3 factorial over the difference. Notice how the formula interpret it. So 3 factorial over the difference, N minus R, over 3 minus 2 factorial. And we know 3 factorial That's 3 times 2 times 1, which is 6, over 3 minus 2, that's 1. 1 factorial is 1. So the answer is 6. And we could have determined, from just listing them out, that there are 6 different numbers you can get. 6 different 2-digit numbers you can get using from the elements 1, 2, or 3. But since the order is important, we use the NPR formula. Let us look at another example. How many different ways are there to select one class president and one vice president from a group of 10 students? So the question is, do we use NPR or do we use NCR? In other words, does the order matter? And it certainly does. Because if you think about it, if you say, yes, let's say you have 10 persons, all right, and you select 2 persons, person A and person B. So let's say person A is the president and person B is the vice president. All right? What would that mean is that you could do a different selection where person B, so person A could be the president and person B could be the VP. But also you could do a different arrangement where person B is the president and person A is the vice president. So in a case like this where there are specified posts, the order would matter. All right, so the number of ways in this case will be 10p2, and applying the formula here, that's 10 factorial over 10 minus 2 factorial. So that's 10 factorial over 10 minus 2 factorial, which is equal to 10 factorial over 8 factorial. And 10 factorial, that's 10 times 9 times 8 times 7 times 6, and you multiply till you reach times 2 times 1, all over 8 factorial. And 8 factorial, that's 8 times 7 times 6 times, and multiply, times 2 times 1. So 8 factorial in the numerator, cancel 8 factorial in the denominator. So we're left with just 10 times 9, and 10 times 9, that's 80. So there are 80 ways of selecting 2 persons from a group of 10 to be president and vice president of the class. Calculate the number of ways of choosing 3 students out of 5 students to form a team for a maths competition. So we have 5 students and we're choosing 3 persons. So let's say we have 5 students, student A, student B, C, D, and student E. And we're to choose 3 students. So if you think about it, let's say we choose student A, D, and E to be on the team. If we should put them in the order D, E, A, then you should ask yourself, is that a different team? Same 3 persons. Let's say this person is Alistair, this person is Damien, this person is Eve. And if we arrange the persons in a different seating, is it a different team? Same 3 persons, so the same team. So in this case, the order doesn't matter. So in a case like this, the order will not matter. All right, because ADA, same thing as DEA, same 3 persons. So when the order doesn't matter, we use the formula NCR, and the NCR is N factorial over the difference, N minus R factorial times R factorial. So here, in this number of ways, here is from 5 persons, we are choosing 3. So that's 5 factorial over 5 minus 3 factorial times 3 factorial. So R, in this case, R is 3. So doing our calculations, we end up with 5 factorial, that's 5 times 4 times 3 times 2 times 1. In the bracket here, we have 5 take away 3, that's 2 factorial, that's 2 times 1. And 3 factorial, that's 3 times 2 times 1. So 3 times 2 times 1 up here, times 1. Cancel with 3 times 2 times 1 down here. So in the numerator, we have 5 times 4, which is 20. In the denominator, we have 10. So 2 times 1, 2. So we have 20 divided by 2. So there are 10 ways of selecting 3 students from a group of 5 students to form a team. Let us look at another problem. On a desk in the library, there are 5 math books, 2 chemistry books, and 4 bio books. In how many ways can the librarian arrange the books so that all the books of same subject are together? So we have 5 math books, so 5M for math book, and we have 2 chem book, and we have 4 bio books. All right, so we look at them as groups. So the librarian wants to place these books so that books of the same subject are together. So if you think about it, it's 3 groups, so 5 math book beside 2 chem book beside 4 bio books. That's 3 groups. All right, so 3 factorial for that. So a number of ways. Let's work it out to a number of ways. So if you think about it, so remember the books of the same subject must be together. So we can start the arrangement with 5 math, or we could put the 5 math at the end and then 4 bio at the front, or we could put the 2 chem at the end or the 2 chem at the front, and so on. All right, so 3 groups, so 3 factorial first. So these among themselves can be represented 3 factorial ways, 3 times 2 times 1, 6 separate ways. Now these 5 math book, if you think about it, these 5 math book within themselves, remember it's 5 different math book, can be arranged in 5 factorial ways since there's 5 of them. And these 2 chem books can be arranged in 2 different ways. So the first chem book can go here, and the second chem book can go here, or it could be the second chem book at the front and the first chem book after there in the middle. So that's two chem books, or 2 factorial ways, and the 4 bio books, bio 1, bio 2, bio 3, bio 4, within themselves can be arranged 4 factorial ways. So 4 bio books, 4 factorial ways, 2 chem books, 2 factorial ways, 5 math book, 5 factorial ways. And then as a group, it's 3 groups, so those 3 groups can be arranged 6 ways, represented by 3 factorial. All right, so do the calculation. So 3 factorial, that's 3 times 2 times 1, that's 6. 5 factorial, that's 5 times 4 times 3 times 2 times 1. That's 120. 2 factorial, that's 2. 4 factorial, that's 4 times 3 times 2 times 1. That's 24. And this should work out to be 34,560. That's a number of ways that this can be done. Next example, in how many ways can we arrange the word gratitude so that all the vowels are always together? So if you look at the word gratitude, how many vowels are there? So we have A, I, U, E. So the vowels there are A, I, U, and E. And the remaining consonants are what now? So we have G, we have R, we have A, no, we have GR, we have A, so G, we have R, we have T, we have 2 T's, and there's a D. Alright, so all the vowels are always together. So we see these 4 characters as one group, as one thing. And so that's 1. And then we have what? 5 consonants remaining. So that's 1, 2, 3, 4, 5. Alright, so all the vowels must be together. So So the consonants, so we have 6 of them, and then this one group of vowels, A, E, U, A, I, U, E. So so in other words, so we view it, let's view it as 6 characters. That's character 1, character 2, character 3, character 4, character 5. Let's view it as 6 characters. All right, so we have 6 characters. All right, 6 characters. So we say A, I, U, E must always be together. So we view it as 1 character. It must always be together wherever in the arrangement they are. All right, so 6 characters. So the number of ways be equal to 6 characters. But within the 6 characters, notice within the 6 characters now, the T appeared twice. So we have to divide by 2 factorial. Because of the 6 characters, one of them is appearing twice. That's the T. Times also. Now, these 4 vowels, which are as a group together, within themselves, within this group now, A, I, U, E, we could also have A, U, E, I, and so on. All right, or we could put the I at the front, I, A, U, E, and so on. So different arrangements within the 4, even though they're seen as one group and are always together. And to account for that, that's 4 factorial. So again, 6 factorial, since we view it as 6 characters, A, E, U, E, A, I, U, E, the vowels are always together, so we view it as 1. And then we have G, R, T, T, D, that's 5 other characters, so in overall, that's 6 characters. So 6 factorial for the number of arrangements. But among the 6, T is there twice, so we divide by 2 factorial to account for that. And we times 4 factorial, reason being A, I, U, E within itself, 4 characters, can be arranged 4 different ways, even though they will always be together. So in calculating, that's 6 factorial, divided by 2 factorial times 4 factorial. So 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1, divided by 2 factorial, so divide by 2 times 1, times 4 factorial, that's 4 times 3 times 2 times 1, that's 24, 24 here, 2 times 1, we'll cancel 2 times 1 up here, so we are remaining with 6 times 5 times 4 times 3 times 24, that will give us 8,640 ways. Another example, in how many ways can we arrange the word baked so that the vowels are never together? All right, so number of ways, if you think about the number of ways vowels are not together, what we can do is find the number of ways total, so the total number of ways of arranging these characters baked in the word baked. So total number of ways of arranging these characters, all right? So total number of ways of arranging these letters B-A-K-E-D minus the number of ways where the vowels are always together. Number of ways vowels are always together. So that's the total number of ways, ways, W-A-Y-S, right? So notice we have 5 characters. So the total number of ways of arranging these 5 characters, and notice all of them are unlike, because all of them are different. So that's 5 factorial ways of arranging all of these letters, right? Now, if we want to arrange them where the vowels are always together, for us to arrange them where the vowels are always together, if you think about it, for the vowels to always be together, so we have 2 vowels, A and E. So if you think about it, so we have B, let's say we have B, K, D, all 3 distinct characters, And for the vowels, we have two vowels, A and E. Let's view it as one group. So the vowels are always together. Let's view that as one group. So we can view it as 4 characters. All right. So B is a separate character. K, second. D, third character. And AE, let's view it as 1 character. So we have 4 groups there. All right. So that's 4 groups. That's 4 factorial to represent that. So number of ways the vowels are always together. Now if you think about it, AE as a group could also be expressed as EA while the vowels are still together. So even among the AE's 2 characters, so can multiply by 2 or 2 factorial, just to account for the fact that AE can be switched around to EA 2 different ways. Alright, so our number of ways, total number of ways to arrange these letters, 5 factorial, since it's 5 distinct characters. Number of ways where the vowels are always together. So we view the vowels as 1 character, AE. So we end up with 4 characters. BK, the consonants, BKD, and the vowels together, AE. But AE within itself can be arranged 2 different ways. Alright, so 5 factorial, that's 5 times 4 times 3 times 2 times 1. That's 120. And 4 factorial, well, the 4 factorial is 24. 4 times 3 times 2 times 1, that's 24. And 2 factorial is 2. So that's 120 minus 48. And that's equal to 72. So the solution to this question, 72 ways to arrange BA, KED, so that the vowels are never together. Next, using the digits 1, 2, 4, 5, 7, 9 and without repetition, how many numbers can be formed which fall between 200 and 700? So obviously, for the number to fall between 200 and 700, it has to be a 3-digit number. Alright, so we think about it. For the number to fall between 200 and 700, 1 cannot be a part of it. 200 and 700. So we rule out 1. 1 cannot be a part of it. Well, 7 cannot be a part of it. And 9 cannot be. So the number cannot start with a 1. Well, it can be a part of it, but not begin with 1, 7, or 9. So for the number to fall, be above 200 and below 700, it has to start with either 2, 4, or 5 from the options we are given here. So 2, 4, or 5. So notice we have 3 options there. Alright, so the number, so the amount of options are 3 options. So the number would have to begin with either 2, 4, or 5. So 3 options. Alright. So remember we have 6 digits. And once we use one of the options here, whichever option, whichever digit we put here, in the second slot, since we have 6 digits, we're selecting from 6 digits, and we have used 1, we are now left with 5 options. And if we use 2 in the first 2 slots, from the 6 in the final, we are left with 4 options. So the number of numbers we can form which fall between 200 and 700 will be 3 times 5 times 4. 3 times 5, that's 15. 15 times 4, that's 60. So there are 60 numbers that we can form using these digits. 60 numbers that would fall between 200 and 700. Now, the question said with repetition, without repetition. What if we're doing it with repetition? Let's see, we can use, in other words, what if we can use a number twice? What if we can use a number twice? So with repetition, again in the first slot, the number would have to begin with, since the numbers fall between 200 and 700, the number would have to begin with either 2, 4, or 5 for it to fall in this range here. So again, 3 options. Now, so we have use an option, and because we can repeat, it's 6 possibilities. Because we can repeat the same number in the second slot, we still have 6 options. And in the final slot, we still have the same 6 options, since we are able to repeat, if we are able to repeat any digit. Alright, but the solution was 3 times 5 times 4, since we're not allowed to repeat a digit. Otherwise, if we're allowed to repeat, the solution will be 3 times 6 times 6, whatever that works out to be. 4 students are to be selected from a group of 7 to form a quiz team. In how many ways can the team be selected if 2 particular students must be included, and part 2, 2 particular students must not be included. Must not. So type right here, must not be included. Let's do part A. So 4 students are to be selected from a group of 7 to form a quiz team. In how many ways can the team be selected if 2 particular students must be selected? So you have 7 students. So the quiz team, let's do part 1 together. So the quiz team must have 4 persons. Now if 2 students must be selected, let's say we have student A and student B to be selected. Alright? So we need to select 2 more from student A. So we have 7 students, and student A and student B are definitely part of the team. Then we are left with 5 students to select 2 from to get the other 2 remaining members. So the concept of this will be 5, choose 2, simply because we're using 5, choose 2, because the order would not matter. Right? So 5, choose 2, that's equal to 5 factorial over 5 minus 2 factorial times 2 factorial. So 5 factorial, that's 5 times 4 times 3 times 2 times 1 over 5 minus 2, that's 3, so that's 3 factorial, that's 3 times 2 times 1 times 2 factorial, that's 2 times 1. So down here, 3 times 2 times 1, cancel 3 times 2 times 1 up here. So solution 5 times 4, that's 20, and 20 divided by 2, that's 10. So part 1, the answer to part 1 is 10 ways. Let's look at part 2 now. So in the second part for the question, if 2 students must be excluded from the team, and remember you're selecting from 7 persons, and if 2 are ruled out, then you're really just selecting from 5 persons now. And how many persons are you choosing from the 5? 4 students. So 5 choose 4. So the solution for that, that's 5 factorial. So 5 students you're really selecting from, since 2 must not be included out of the 7. Alright, so you're really selecting 4 students from 5. So 5 factorial over the difference, that's 5 minus 4 factorial times 4 factorial. Now 5 factorial, that's 5 times 4 times 3 times 2 times 1 over 5 take away 4, that's 1 factorial, and 4 factorial, that's 4 times 3 times 2 times 1. So 4 times 3 times 2 times 1 down here, cancel with 4 times 3 times 2 times 1 up here. So you're left with just 5 over 1 factorial. That's 5 divided by 1. So there are 5 ways of selecting a team of 4 from 7 students if 2 out of the 7 must be included. So out of the 7, you're really only selecting from 5. You're selecting 4 students from 5 students. Let's move on. there are 15 persons in a school club, 5 of which are boys, 6 are girls, and 4 teachers. The club members want to select an executive committee of 3 girls and 2 teachers, or 2 girls and 3 boys. In how many ways can this be done? So remember, based on probability theory, we see and, we multiply, we see or, we add. So the club members want to select an executive committee of 3 girls and 2 teachers. So 3 girls. So how many girls do we have? So the solution here, how many girls do we have now? We have 6 girls, and from the 6 girls, committee want to select 3 of them. So 6 girls, choose 3, and 2 teachers. How many teachers do we have? 4 teachers. So from the 4 teachers, we're choosing 2. Or, so we have plus for R, are 2 girls and 3 boys. So 2 girls, how many girls again? 6. So 6, choosing 2 girls and 3 boys. And how many boys we have? We have 5 boys. So from the 5 boys, we're selecting 3 boys. So that's 5, choose 3. So again, we're selecting 3 girls from 6 girls and 2 teachers from 4 teachers, or we're selecting 2 girls from the 6 girls or 3 boys from the 5 boys. So let's do the calculation here. So 6 choose 3, that's 6 factorial over 6 minus 3 factorial, so that's 3 factorial times 3 factorial times 4 factorial over 4 take away 2 factorial times 2 factorial, or so plus 6 choose 2, that's 6 factorial over 6 take away 2, that's 4 factorial times 2 factorial times 5 factorial over 5 take away 3, that's 2 factorial times 3 factorial. So the calculations. Now 6 factorial, that's 720. 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial, that's 6. 3 times 2, 1, that's 6. So that's 6 times 6, that's 36. Times 4 factorial, that's 24. Over 2 times 2, that's 4. Plus 6 factorial, that's 720. Over 4 factorial, that's 4 times 3 times 2 times 1, that's 24. Times 2, that's 48. Times 5 factorial, that's 120. Over 2 times 3 factorial, that's 2 times 6, that's over 12. And this will work out to be 270. So there are 270 ways of forming this executive committee based on the way it was specified. In a room, there are 12 persons. All of them decided to shake hands with each other only once. How many handshakes took place in the room? So there are 12 persons, and of course it takes 2 persons. It takes 2 persons to do a handshake. So we have to ask a question: do we use NCR or do we use NPR? So if you think about it, let's say person A and person B shook hands. So person A and person B, what if the other way around? Same two persons shaking hands. So it doesn't matter, the order does not matter. So we use the NCR. So the solution here, the number of handshakes would be 12, and we're choosing 2. So this is 12 factorial over 12 take away 2 factorial, that's 10 factorial, times 2 factorial. So that's 12 times 11 times 10 times 9 times 8 and so on. So that's times 10 factorial. In the denominator, we have 10 factorial times 2 factorial, which is 2. So 10 factorial up here, cancel 10 factorial, and 2 into 12, that's 6. So our solution there would be 66. So there are 66 handshakes if we're not counting twice, all right? Well, sorry, or if you're not supposed to shake hands twice. So notice, very important, they're only allowed to shake hands once. And that's extremely important. Next. How many 4-digit even numbers can be formed from the digits 5, 6, 7, 8, and 9 if the number should start with 7? So 4-digit even numbers, so 4 digits, so we have 4 slots. Now we're told that the number must start with 7, so that's one option there. So the number should start with 7. That's one fixed option there. Now for the number to be even, it has to end with either 6 or 8. By the way, we're looking at a case where we're assuming that repetitions are not allowed. Alright, so we assume that repetitions not allowed. So in other words, we can't use a number twice. Repetitions not allowed. So for the number to be even, it has to end with either 6 or 8. 6 and 8 are even numbers, right? So at the end, we have 2 options. So 6 and 8, we have 2 options. Now, if a number starts with 7, and we put an even number there at the end, from the 5, we're left now with 3 options to put in the other slot. And then, if we use 3 options, if we already use now 3 options from the 5, for the final slot, we're left with 2 options. Alright, so the first slot, 1 option. Final slot, we have 2 options there. And once we use 2 numbers rather, in the first and the final slot, in the second one, we have 3 options from the 5 remaining. And in the second to last slot here, we have used 3 options already. So we're left with 2 options now. So the solution would be 1, we're multiplying the options, that's 1 times 3 times 2 times 2. So 3 times 2, 6. 6 times 2, 12. So we can form 12 4-digit even numbers from these digits, 5, 6, 7, 8, 9. Now what if repetitions are allowed? So look at the case where repetitions are allowed. The question did not specify. What if repetitions are allowed? So it's a 4-digit even number, and again, it has to start with 7. So that's one option. Must start with 7, and must end with an even number. Well, the number must be even, so it has to end with either 6 or 8. So in the final slot, we have 2 options. Now, so of course, we have used 2 from the 5, but repetitions are allowed. So in the other slots, we still have 5 options, since repetitions are allowed. So the solution for this case would be 1 times will be 1 times 5, we're multiplying the options, times 5 times 2. So 5 times 5, that's 25, times 2, that's 50. So if repetitions are allowed, there are 50 4-digit even numbers that can be formed from these 5 given digits. A vault has a 3-digit password. Paul could not remember the password and decided to try all possible combinations. So the password 3 digits. And Paul could not remember the password and decided to try all possible combinations. He took 5 seconds for each attempt. How long will it take him to try all possible combinations given that the digits could be any from 0 to 9? So 0 to 9, that's how many digits? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 to 9 and 0. So there are 10 possible digits that would form this 3-character password. All right. So of course, let's assume that the same digit can be used twice for the password for this vault. So in the first digit, for the first number in the password, there's 10 options, 10 possibilities. Likewise, second option. So in other words, if I use 1, then the second digit in the password could also be 1. So 10 options in all combinations, right? So 3-digit password, and each slot, we can have 10 possibilities. Since, of course, we're assuming that a number can repeat in the password. So a password, for example, could be 222. Or a password could be 333. Alright, so if I use a digit in the first slot, it can also be used in the other slots. Alright, so the number of possible combinations, 10 times 10 times 10, that's 1,000 different passwords, 1,000 combinations. If you should exhaust all the combinations. Now the question asks, how long will it take him to try all possible combinations, given that the digits could be any from 0 to 9? So there are 1,000 possibilities. He's taken 5 seconds for each attempt. So time required to try all combinations. Remember, it's 1,000 of them, and he's taking 5 seconds for each. So that's 1,000 times 5. That's 5,000 seconds. And of course, if you want to convert 5,000 seconds to minutes, we can divide by 60. So if we divide 5,000 by 60, that seems to be 83 1/3 minutes. Next, in how many ways can 6 persons stand in a circle? And the formula for that, in a circle, it's n minus 1 factorial. So the number of ways 6 persons can stand in a circle is 6 minus 1 factorial. That's 5 factorial, which is 5 times 4 times 3 times 2 times 1, and that's 120 ways. I sincerely hope this video has helped with our understanding of computing permutations and combinations problems. Goodbye.